Howdy, we are doing properties of exponents and radicals. They follow the same properties even when they are higher degrees or weird rational fraction exponents. So let's start with the exponents on rational exponents. So the power property and the product property still apply here, where we add their exponents if they are the same basis. Sorry, that is just the product property. So we'll add 1/2 plus 1/4, and that gives us 3/4. We can also use the power property where we multiply their exponents. And in this case, that helps us because it gives us a whole number exponent, which is a little bit easier than trying to find the square root of 6. So this ends up being 6 squared, which is 36. We're going to use a variant of a power of a quotient, and we're going to reverse that. We're going to say, hey, let's say that whole thing is being raised to the 1/3, and we can simplify the fraction. Now this gives us the third root of 8, and if you need some convincing, the third root of 8 ends up being 2. So let's get into multiplying and dividing. All right, in order to do pretty much anything with radicals, we need to make sure the indexes are the same. So here we have 2 square roots, and I'm going to start by simplifying the root of 350 down to 5 root 14. Again, the square root of 25 is 5, and that's how I got that. Now, if I simplify root 14 a little more by factoring it down, the whole expression has 2 root 2's in it. And root 2 times root 2 is just 2. So 5 times 2 now is 10, and I get 10 root 7. I could have also started this problem by multiplying the 2 and the 350 to 700, and that would work as well to start the problem. So I'll do that here. 9 times 6, I'm going to just go ahead and call that third root of 54. Now since it's the third root, I'm going to look for perfect cubes is one method of this. So 27 is a perfect cube, meaning that if I break it up into 27 and 2, which is 54, then I know this cube root of 27, which is 3, and I can simplify that part of it. The other method would be to start factoring everything. So if I factor down 9 to its roots and 6 down to its prime factors and combine everything, I see that there are 3 root 3's underneath the radical, and those can form a full number. So my final simplified solution is 3 times the third root of 2. So on this next one, I'm going to put them both under the same radical, and then that allows me to simplify it. So 96 divided by 2 is 48, and I'm going to again use a prime factor method. And what I'm going to look for, oops, I missed, it's actually root 4, so I got to make sure the index is how many of those same numbers I'm looking for. And that gives me 2 to the 4th underneath the root, and a 4th power and a 4th root cancel out perfectly. So my final solution here is 2 times the 4th root of 3. The 3 is left over because we couldn't take a 4th root out of it. There was no power there. I'm going to use a little bit different of a strategy here with higher exponents. Remember that we can rewrite exponents in a lot of different forms with the same base. So like I can rewrite them as product property or power properties, and those will all help us at different times. But viewing these ways will help us. So I'm going to look at the y to the 6th is actually 2y to the 3rds. And I could think of that as y to the 3rd squared, or reversed y cubed squared, or y squared cubed. Either way works. Now, 64 is 4 to the 3rd. So what I'm seeing is I have a bunch of third powers here. And third powers cancel out with third roots. So I have 4 times y squared as my final solution. So with a quotient like this, and since everything's under the same radical, I'm going to go ahead and I'm actually going to try this 2 ways. I'm going to split it into a radical of the top and a radical of the bottom. The top one cancels out perfectly, it just becomes x. The bottom one I'm going to rewrite as x squared to the 4th. I chose the 4th power on the outside, so it would cancel out with the root. And in the end, I simplify using the quotient property of exponents. So the strategy I'm going to use here is I'm going to look at the index, and I'm going to kind of similarly also, if I can simplify like 32, I'm going to call it 2 to the 5th, which is true. 2 to the 5th is 32. So what I'm going to do every time is I'm going to look at the index and see how many times that goes into the exponents there. So 4 goes into 5 one time with one remainder. So I'm going to bring out a 2, just 2 to the 1st, because it goes in one time. And what's left over is also 1, 2. And I'm going to do this again with the a to the 5th. So 4 goes into 5 one time, so I bring out an a and there's 1 left over. On the next part, 4 goes into 12 perfectly 3 times, so I'm going to bring out a b to the 3rd is what's left over. And the c, 4 goes in there twice into 10, but there'll be 2 left over, so I'm going to give myself some more room here. And so every time I'm just looking to see how many go in, and then I'll leave the remainder on the outside of the exponent. So the remainder will go on the inside of the root. So here's my final solution. I'll write this a little cleaner. Again, the 4 went into the 5s one time, so that's why there was 1 left over each time, and the 4 went perfectly into the 12, and it went twice into the 10 with 2 left over. So that explains the exponents. So let's try that again with this next example. So my strategy will be to start by looking at that negative 27 and calling it negative 3 to the 3rd. And the rest are already in their exponents. So every time I'm going to look at how many times does 3 go into the exponents, and that's the power I'll bring out to the outside, and the remainder gets left in. So the negative 3 perfectly comes outside. 3rd root and a 3rd power cancel out. On the next one, 3rd root goes in only 1 time to the 4th power with 1 left over. Same with the y, goes in 3 times perfectly, and then the z goes in 3 times, but there's 1 left over. So that's 3 times 3 is 9. There's still 1 z to the power of 1 still left underneath. All right, so adding and subtracting radicals, we need to think of these like terms. So if we can get them to be the same root and index in each term, then we can just add their coefficients. Now, that's again like when I do 3x plus 2x equals 5x, same idea. So since the 3rd root of 2 is the lower one, I'm going to simplify the 3rd root of 54 down to 3 3rd root of 2, and now they match. They both have the same radical. So I'm going to think of it as like 3 minus 1. I have 3 3rd roots of 2 minus 1 of them, so that leaves me with 2 3rd roots of 2. So similar idea here. So each time I'm going to simplify, and if the radicals match, then I can subtract their coefficients. So I'm simplifying here. You might need to look a little more, and I get extra practice on simplifying higher order radicals. But anyways, I get 8x times the 3rd root of y plus 7x times the 3rd root of y. So I just add the 8x and the 7x to be 15x. And in the third example, again, I'm just simplifying each of them. Now this time I have to simplify both of them. And we always want to try and get them as simplified as possible. And that will indicate whether we can or can't add them. So if they have the same root is the key when we can add or subtract the radicals. So somebody decided a long time ago that they don't like radicals in the denominator. And so something simple like this, it's hard to divide by a radical. So one strategy is to multiply by an identity of 1, and ideally it's the root over itself, because that will cancel it out. But then sometimes you get to something like this where it's more of a 2-term thing, and that same strategy won't work because you'll have to distribute that root into there, and it doesn't work. Oh. So here's what we're going to do. We're going to use something called the conjugate, which is the opposite sign as the denominator there. And it kind of bases on the idea of the difference of squares, and allows us to avoid that weird kind of middle term as well. So on the top, I just distribute. It's a 1, so that's pretty easy. And on the bottom, while I can distribute this in, like FOIL it out, or however you want to say, my pen is dead twice. I'm going to use the difference of squares identity, since they are the difference of squares, and it's 1 squared minus root 5 squared. Now what's cool about that, root 5 squared is just 5. So that gives me 2 whole numbers, no more roots in the denominator. The top can have anything up there, but the denominator needs to not have any roots. And I've accomplished that goal. Same thing here on part B. I simplified a little bit differently. So I used the conjugate. So I use 3 minus root 7 instead. I have to do a little distributing on top. And here we go. I get down to this. Now, there's a couple ways to simplify it. And when I get towards the end of the problem here, I realize it would have been easier to simplify If I actually didn't distribute the 2, if I just left it out there because it would be a common factor, I could do it like this. 2 times 3 minus root 7, and there's a 2 there. The 2's will cancel out, divide to 1, and I have a final answer of 3 minus root 7. So there you go, some different properties. You're probably still going to have questions. If there were mistakes, let me know. We can add those. So check the comment box or the description if there were mistakes in this video. And again, you're not expected to master this after one go. Have the examples written down and we'll work through it in class.